Hi, do you see my screen?
Yes, we do. Not
Thank
in
you.
the presenter mode though, but yeah, there we
But
go.
now it's good, yeah?
Yeah,
Awesome.
perfect.
Okay. Hi, everyone. Good evening for the European people. Good afternoon for the East Coast folks. Yeah, thanks first to Thomas and Dennis for giving me the chance to present here and also for staying for this. Um, So we'll see actually what this is going to be. It's very undefined as you will see, and so most of what I'm going to talk about is actually mostly motivation. Actually, what brought me to talk with both of them at Exo5, like Tuma mentioned earlier, and what I had so far thought about, and what we had discussed in this group there that is mentioned here on the page about this potential intercomparison protocol. And then I'm actually very interested in hearing your thoughts on this, and also I'll talk about the timeline. Oh, all right, let's go. So so the general motivation for these types of things is sort of from an Earth-based perspective, how do prebiotic environments form and evolve? Simply because the transition from the early magma ocean phase after the moon forming impact to a clement state is really a coupled process between the degassing of the atmosphere, the loss to space, and all those things happen at the same time scale. So the why my title actually didn't say necessarily interior, but magma oceans in particular, is that there's good grounds to believe that actually this magma ocean phase is the defining aspect of planetary evolution, specifically in terms of volatile partitioning between the interior and atmosphere of rocky planets. And so I'm talking mostly about rocky planets, and as I said, I will talk mostly about the motivation for this, so that when I come at the very end toward the pre sort of the thoughts that I've given to this so far, and that we can discuss a bit about about the specific processes that I aim to tackle with this. And so this here, what you see is sort of a wheel of time from the accretion stage to the secular geodynamic evolution stage. And this stage here in particular is the magma ocean phase, when the rocky mantle of planets is entirely molten by accretionary heat from formation. Um, and as I will show on a few slides from now, this stage is defining in, first of all, forming the core. But for the atmospheric folks here in this meeting, it's really sort of establishes the fractionation between individual elements, between the mantle, the core, and the atmosphere. So whether a rocky planet, the secondary atmosphere is sort of oxidized or reduced is determined during this phase. Now, this ties very much together actually into other MIPs of this workshop, because the sort of models that we use in the community to calculate this phase actually are based partially on several of the other processes that are targeted with in other MIPs here. And so this here is just an example of the runaway greenhouse. So this here, well-known plot mostly all you certainly have seen. Many of you have seen this plot. So this is top of atmosphere flux, surface temperature, and this is the thermal limit essentially for pure steam atmosphere, 260 bar. This defines, based on Ravi's website paper from 2013, is often used to define the inner edge of the habitable zone. An interesting aspect about this, which feeds into the motivation of this protocol idea, is that actually this curve is only really valid for a fixed surface pressure until about this point here, because beyond that, if your atmosphere is convective, then the surface temperature will rise above basalt melting. Now, not everyone in the community thinks so, of course, and so there's very interesting work in France on this. So in Celsius, for example, some of the authors who are here in the audience argued that actually under these conditions, the lower atmosphere and the steam atmosphere is radiative, and you do not actually at the base of the atmosphere, you're actually below the solidus of the mantle, and that would mean you are actually solid in a steam runaway greenhouse phase. Now, What I would argue is that actually it's a coupled process. So you have to model both the interior and the atmosphere in order to answer that question. And so whether you come from the right or you come from the left on that curve is actually changing the outcome of your simulation to some extent. And so this is the type of question that we want to tackle, at least from my perspective so far, in this protocol. Or this is one of the questions that we would want to look at in what different models type produce as an outcome for this. So why is this so critically important? Actually, I just want to come back for this for the people who are not who are mostly focused on the atmosphere. From a geophysical or geochemical perspective, so gases partition like to dissolve in liquids. This is true for the CO2 in your Pepsi Coke, but it's also true for water in a magma ocean atmosphere. So different gases, different compounds have different solubilities. Water is highly soluble in silicate magmas, for example. So this here on the y-axis, the volatile solubility in parts per million weight relative to the mantle. This is gas phase pressure, and you see how different types of compounds here have orders of magnitude differences in their solubilities. And what does it mean if you have a coupled system of a liquid, mostly liquid mantle and an atmosphere, then you will dissolve those volatiles into this liquid. And this creates like an emergence phenomenon, which how I like to call it, because it's actually really qualitatively changing the behavior of the system. So let's assume you have your given atmosphere molten mantle. You increase the thickness, then you increase the greenhouse effect. That actually increases typically the trapped heat by increasing the opacity of the atmosphere. Now, if on the other hand the mantle solidifies, actually would solidify, because if you have emission to space, then you lower the amount of melt in the mantle, and that pushes some of the volatiles out, because the volatiles, in particular water, for example, are not soluble so much in rocks, actually, in solidified rocks. And so you increase the opacity of the atmosphere again, and that increases the greenhouse effect, and that increases again the melt volume in the mantle. And so there's a loop, and this loop actually is very, very tricky in time evolution models to capture. This is not the only thing, because it's actually not that simple. Mantles are very, very complex entities. They would require actually GCMs for themselves, and they exist, but that's not what we're going to focus on. Mantles do not necessarily crystallize very simplistically from the bottom to the top, but they can crystallize somewhere in the middle. We have increasing evidence for this from the Earth and from Mars, and also some circumstantial evidence from Venus that this happened in the past. And if that's true, then we really have a problem, because if the mantle somewhere is cut in the middle, and it solidifies from the middle out, and from the middle up downward, then the vast majority of initial volatiles that are accreted onto a planet during planet formation is actually trapped in the interior of the planet for potentially billions of years and can degas later. So I just will show a few cases why this is so timely. This here is the famous, infamous, I don't know on which side of this debate you stand, emission spectrum of 55 Cancri from earlier this year, where the authors surprisingly couldn't fit the data they received, whether you believe this data or not, couldn't fit it with a pure rock vapor atmosphere. So they suggested instead that the data that you see here would fit to a volatile-rich atmosphere, which would be very surprising if you consider that 55 Cancri is a highly ultra-short period super Earth that is certainly way above the liquid temperature of these rocks. Now, such type of result will be certainly contentious at the moment, and we'll see for other planets what appears and for future data that is taken for this planet. Now, that is contentious from data perspective, but conceptually this makes sense actually, because if your mantle is largely molten, then it is a huge sink for atmospheric volatiles, in particular water. and also carbon, and also nitrogen. And so this is a mass radius plot here. Radius, mass, Earth is somewhere here, down here. And 55 Cancri is here. And the line you see that goes through this planet, like a few others, is one that is a sort of an Earth-like composition with about 5% of water mixed in. And so this can explain the mass radius curve and also, for example, the retention of volatiles in these planets, if there are some. I guess TBD. Another high-profile case from last year was the sort of interpretation of the TRAPPIST-1c planet. And so this is a plot from SIBA 23. Initial water abundance here. This is the assumed XUV saturation fraction. And the color is the oxygen partial pressure. And so these are essentially models, magma ocean evolution models, coupled climate interior models that are time evolved. And the outcome of these simulations is sort of a prediction of the buildup of abiotic oxygen, where sort of water escapes, so water is photolyzed in the upper atmosphere, the hydrogen escapes, and the oxygen stays over. This is another case. Another one is K218b. Actually, so here this is the transmission spectrum of K218b from last year. Methane abundances, carbon dioxide abundances, which was used to claim like a surface ocean, and there's also some debate about life, even because of this 1 sigma DMS detection. Sorry, I need to go back. One of the key parts of this here is the absence of ammonia, and in a paper led by Olli Schortel, he showed that actually this is a natural consequence if all sub-Neptunes are internally molten, because nitrogen in a reduced cis chemical system likes to strongly partition into silicate liquids. And so what you see here is the atmospheric nitrogen fraction. This is the magma ocean, so-called redox state, which you can think of as sort of composition. To the left, it's more hydrogen rich. To the right, it's more oxygen rich. And you see at highly reduced chemical compositions, which we expect for sub-Neptunes, actually most of the nitrogen will go into the magma ocean. It will naturally explain the spectrum that we see on K218b without invoking surface water oceans, for example. Then what I haven't talked so much about yet is that time evolution is key. Of course, we know that escape, at least to a certain extent, shapes the exoplanet population. This is just a plot from Rodrigo Luga and Rory, who is also here in the audience, I think, from some time ago, suggesting which essentially made these predictions seminally for that sort of huge loss of water can potentially lead to oxygen buildup. And so there's a substantial time component involved. We cannot look at these systems in isolation at steady state, but we must consider sort of the history because of this coupled effect between the interior and the atmosphere. And this has just recently, actually, because of this urgency now with JWST, has sprung into a flurry of different types of models. Here from the vPlanet model. This is from Pac-Man, from Josh Christensen Totten. This is from the Cowan group. I'm sorry I couldn't mention all. These are just the ones that I found earlier today and that I remembered to put on the slides. There's another one from Maxime, also here in the audience here. So there's a flurry of models, and no one has ever tested whether they agree. So the time evolution of these models is really key because for different geological time intervals, and especially the ones that we observe in present day, the models very likely makes drastically different predictions. And this very last slide here is talking about that the predicted compositions of these atmospheres from different types of models differ substantially. And I think that brings me to my officially last slide in principle, but I will spend a bit more time on this one. That brings me to the motivation behind this. So the general idea comes for Thomas mentioned. So we're waiting for the outcome of the proposal for which has a relatively good chance of being accepted. Fingers crossed. which is in Leiden, in the Netherlands. And the idea here is to use this workshop sort of starting ground for in-depth discussion on the protocol and also on the implementation of the protocol, I presume. So the workshop is supposed to be in September 2025. It is relatively limited in person space because of the geometry and the meeting hall is at 25 people. But limitless essentially in virtual participation. So we will make sure that there's it's accessible virtually. Dennis will kindly agree to help with this and relay specifically with the CUISINES network. Yes, and then the idea is sort of that we draft the protocol sometime in fall 2025 and implement it in the following time. So the right-hand side is sort of what should roughly be covered from my perspective. We really haven't gone into detail of this, and so I felt a bit, volunteered, I would say, to give this workshop. But I think, as Linda said earlier, maybe it's a good idea to start thinking about this earlier, and also to get feedback from the CUISINES network overall, to maybe what is a good idea to start with. So what I thought about before so far is really specifically the effects, the coupled effects of time evolution of the interior and atmosphere together. There are some things that we want to focus on which are a bit more isolated. For the atmosphere, that would be main constituents over time, general climatic characteristics like TPX spectra, interior, the total amount of installed volatiles, the total time it takes for the planets to crystallize, and other geophysical quantities. Maybe for the planet overall, generally the energy balance over time, emission characteristics, redox state and composition, and the overall evolution. Now, interestingly, when we heard Linda's talk earlier, talking about being data starved, that's true, of course, but in this particular protocol, I think there's a sort of weird corollary of this. We are sort of data starved, but also there's actually, from a geophysical perspective, there's lots of very detailed data, and everyone just takes something and uses and imports it into their model. So I anticipate then this MIP, we will have to spend a considerable amount of time actually on just understanding what type of assumptions we use in terms of data, in terms of thermophysical properties. And yeah, I think I want to stop here. Thank you so much for your attention. I'm happy to take any questions and discuss about these plans. Thank you.
Thank you very much, Teamwork. That was super interesting. Thank you. Do we have questions from the audience? See, we have one from Prabal in the chat. Prabal, are you able to say it out loud, or I'll do it for you?
Sorry, Thomas. I'm happy to ask. Tim, thank you so much for that talk. So for the models that you mentioned that kind of have all these time sensitive atmospheric evolution models, do they have control cases without XUV driven atmospheric escape or other space weather mechanisms? Do they have, I'm sure some of them have different flavors of escape in terms of how they prescribe it as well.
Yeah, well, so I think that's one of the things. So I think some of these models actually, so most of these models use very limited very simplified prescriptions for escape in general. Mostly use energy limited escape actually. Some use, well, maybe one or two actually use is some sort of fractionation in the escape, which is essentially by drag of, for example, that higher mass constituents in the outflow are dragged together with the hydrogen. But actually, there's very little on terms of reduced compositions. So what we will certainly will do is we'll shut off escape and compare the models without escape, because I think that's sort of the baseline case we definitely need to start looking into, because escape can probably dramatically change the outcomes. Yeah.
Thanks, Tim.
Emeline?
Hi, Tim. Thank you for the nice talk. I had a question for you. So I guess that, like we are doing for the climate, you're envisioning doing this comparison first in 1D and maybe later with more complex models. Do you already have a plan on the way you you
I
want to do
honestly don't think you can do this in more than one dimension, because the timescales we're talking about are hundreds of millions of years. Yeah, I haven't seen a coupled time evolved evolution model that works in more than one dimension, to be honest. I think it's different to what like Guillaume said, right? Time marching. That's not what I mean. I mean really time evolution, like starting at let's say 100 million years after star formation and go to a few giga years or something like this, depending on the ambient environment. So I do, do you know do you think that that's doable in 2 or 3D?
I know that there are some efforts in Zurich with the, Paul Taclay, Loïc Pellissier, who are trying to do that in
Oh, I
a bit
see, I
more than
see.
1D at least. But
So that's what they do. Okay. What they do
but,
is
but
actually
maybe it's not Magma Ocean, sorry. Maybe it's
yes,
not Magma Ocean, yeah.
exactly. It's
Mm.
solid state convection where they sort of like have a two-dimensional geophysical solid state convection model, and then they stop the model for some time, then do recompute a steady state atmosphere. I think that's very interesting. But that's not the focus of this, I would say. But yeah, no, good point. Yeah, maybe I should get in touch with them. I don't know. Yeah.
Okay, thanks.
Any other questions? I have one again. So do this model include the tidal heating? Because I mean, I think it's likely very essential for those very compact system, 55 concrete, the TRAPPIST one. So, and although since you're looking for the evolution over time, is it also something that would be parameterized as all tides will eventually change over the age of the system?
So many of them don't.
Mm.
Many of them don't. That's certainly a big mishap of some of these models. Maybe probably Rory's does. I don't know. But as far as I understand, most of these models don't. And actually, so that's why I say like these are just ideas at the moment that I have, because I think we will have to focus on one or two or three aspects specifically. And I think there's such a flurry of what can do, and the focus of this workshop will probably to narrow that down. And Rory probably wants to comment on the title question.
Yeah, might as well turn on my camera early.
Exactly.
Yeah, to answer your question, Tomas, we did look at it, and you too, Tim, we did look at this in the Barth et al. Paper that Tim mentioned earlier. We found actually that tidal heating didn't really have a big role to play in terms of the longevity of the magma ocean. It can't provide enough heat. Part of it is that you just need a huge amount to melt the rock. But also, once you get some melted rock in there, you tend to dissipate, or yeah, maybe I shouldn't use that term. You diminish the amount of tidal dissipation just because it's more liquid. So it's not quite, there's not as much friction as when you have a solid planet. So you really just, yeah, so we really found that tidal heating, unless, I mean, it could, of course, in some cases, like very large eccentricities, be large enough to really prolong a magma ocean, but it really turns out to not be that important. And certainly for the TRAPPIST-1 planets that we were looking at specifically in that paper, where the orbits are all quite circular, just the tidal heating just wasn't that significant.
I see.
But it looks like there are some other opinions.
Maxime, Emeline, one of you?
Go ahead, Maxime.
Okay,
I
thanks.
already asked a question, so.
Thanks, Emeline. I'm going to be quick so that you can ask yours as well. Thanks, Tim, for this presentation. That's a very exciting project. I was wondering if you had already thought whether you wanted to frame it more in the context of highly irradiated planets and highly irradiated magma ocean, or magma oceans on young planets which are due to their hot start. And that's two cases which I guess can be different. And one could be more directly relevant for observation for the high irradiated one. And another one is of course very interesting for origins purpose and questions.
No, that's something to be defined and to be discussed. I mean, we have been in contact about this already. Yeah, and that's, I think we have to limit us to something. I think for I think ultimately those two cases belong to each other, and I think they are much more interconnected than we currently are, in papers acknowledged. But I agree that there's probably technical limitations of doing both. I think we have to focus to some extent, but I don't know which one it should be.
Okay, cool. Thanks.
Emily?
Yeah, I just wanted to get back quickly on the tidal heating points. So even if the tidal heating is not, sufficient to melt stuff or something like that, we had actually an EC workshop not too long ago about a bit this question. But if you have sustained tidal heating for a very, very long time, it's going to impact also the composition of the material that is outcast. Like we see, for IO, IO is mostly expulsing SO2, while probably in the beginning it was not, putting SO2 on the surface, but maybe more CO2 and stuff. So I think there is still maybe interesting stuff to do with this tidal heating, even without melting a lot of the planets. Just a comment.
Thank you.
Yeah.
Okay, so almost I just wanted to follow up on two points there. So concerning the question of Maxime, that means that if you either choose to do the young planet, young star system, or just really the highly irradiated one, that will define whether you do it around a specific type of star, like M dwarf compact, system, or if you do it around G stars as well, right? So. And that means in terms of computational resources, how quick or slow are these models? Because in the framework of cuisine, as Linda mentioned earlier, you can have some completely different experiment. One could be young system, and one really highly irradiated, even old. But that's doable if the model can, do it that relatively fast. But if then it's a huge computational burden to do that, then it's maybe out of the question.
So I think, like so far, at least, and I'm looking forward to hearing more from other people, I really think that these evolutionary aspects play a huge role in a sense, and so like I said before, we only have these coupled models in a sort of 1D fashion. We don't have them really in a multi-dimensional, and they are relatively quick.
Okay.
So one could imagine setting them up for different purposes, but I really do think that these models that I was talking about and mentioning here throughout, they have limitations, especially in interpreting, ultra short period exoplanets, where sometimes geometry plays a role, and depending on how you see your transit or emission feature. Yeah, but I think it's open at the moment to both. Maybe there we can find some cases where this particular steady state situation can be handled by some of these codes.
Yeah.
I think it would certainly be very interesting. Star, I don't think that's such a big problem as you may imagine it, because the models are mostly too simplified to really do complicated atmospheric chemistry or something like this. So it's I think it's mostly energy balance in a sense, like having the volumetric luminosity of the star counts, and not so much the specific spectrum. I think the models are evolving in that direction, but maybe Rory wants to go, or someone wants to correct me, but I think for most of them it's not super important at this point.
Okay. That's great. Yeah, thanks. And then as we have done in other ExoMIP, one model does not have to do all the test cases.
Exactly.
So.
Absolutely. Thank you. Yes.
Yeah, thank you. And thanks to the survey we had for the registration, we have the list of people that express their interest of the interior one. So I'm going to send this email list, and I'm going to do the same actually for all of you chefs here, and for the folks that have expressed their interest to join your intercomparison. So at least you can, then after reach out to them.